Hey everyone, in this video we'll learn how to use Kruskals algorithm. Kruskals algorithm is meant to find a minimum cost spanning tree in a graph. So we have a graph here, and there are a bunch of costs on the edges, or sometimes they're called weights. And our goal is to find a spanning tree, which means, for one, it's a tree, so no cycles or circuits. And for two, it's spanning, which means that every vertex is contained within that tree. And also we want the cheapest one possible, where cheapest means the sum of all the costs on all the edges. So Kruskal's algorithm is a greedy algorithm, but surprisingly it actually gives the minimum cost spanning tree, not just a cheap one. So let's go through this example. And since Kruskal's algorithm is a greedy algorithm, we just keep choosing the cheapest possible edge that we can at each step until we find a spanning tree. So what we do is, at first, we scan all the weights, all the costs, and pick the cheapest one. So we notice there are a couple of 2's here, and I can pick whichever one I want, so I'll pick this bottom one. And then I keep scanning at each step and I pick the cheapest possible edge, so I'm going to pick that other 2. Since these two edges, they don't intersect, and so they're not going to form a cycle. So proceeding in this way, we pick the 3. It can connect to edges that you've chosen, like these two. You just don't want to make a cycle in the edges that you've chosen. So we have some 2's, a 3, here's a 5. And the next weight is a 6, so we can choose this one. We've now connected these two parts, but we still don't have a cycle. We have some 7's. In fact, we have 2 7's, and I can choose either one, so I will choose this one. And then actually it's okay to choose this one as well. We have an 8 here, here, and here, so we have 3 8's. Let's notice that this one is unchoosable, it's not an option. And the reason is, if I chose this edge for my tree, I would create a cycle. That triangle is a cycle. So I can't choose that one. This one's okay to choose, and this one's okay to choose. So I take those 8's. And then I have a 9. This 9 I also can't choose because that would create a cycle. That would be this cycle here. That's a 5 cycle. So I can't choose that 9. The next one is 10, the next cost, and I have a lot of 10s. So this one's off limits, that creates a triangle right here. This one will also create this 4 cycle, so I can't choose that. But I can choose this 10. No, scratch that. I can't. I was thinking this was 10. So I can't choose this 10 either because that would form a 5 cycle. So in fact, all the 10's are off limits. Okay, how about 11? This 11's okay. And is this one okay? Yes. No cycles created. So notice as I build this tree up, I keep connecting various parts, and in fact at this point all of the vertices that are coming into contact with one of the chosen edges, they're all connected. And so I can save myself a lot of work by just recognizing that all these edges that I've chosen, they're all one piece, one connected component. This vertex is the only one that still needs to be included. So what I need to do is choose an edge that connects this vertex to one of these other vertices. So we're just kind of taking a shortcut. And the only way that I can connect this vertex to the rest is by one of these 3 edges. So I just pick the cheapest one, which is 12. And that finishes the algorithm because the edges that I've chosen form a tree, no cycles, connected. And all the vertices in the original graph are contained within that tree, therefore the tree is spanning. So what I have is a minimum cost spanning tree. And the actual cost of the tree we can compute. The actual cost is the sum of all the weights on the edges. So we just need to go through and compute all those. So we have 2, a couple of 8s, that's those edges, and then an 11. You just go through these systematically however you can. 11, 6, 5, 2 7s over here. This 2, and a 12, and a 3. And just to make sure that I got everything, I'll count the number of numbers here, and it should be the number of edges here, which is 1 less than the number of vertices. That's 12 numbers. Let's count the number of vertices. 13. So I got all the numbers. All the costs are here. So the cost of the tree, or the weight of the tree, is just this sum. So again, this is Kruskal's algorithm, and it gives us a minimum cost spanning tree. This is the cheapest spanning tree that I can get. One thing to note is that this tree is not necessarily unique. There could be another tree that is still a spanning tree of minimum cost, meaning the same cost as this one, but it may not contain all these exact edges. And that's because we had to make a couple of choices along the way, like certain 10s or certain 11s. So it's not necessarily unique, but that's our tree.